Yeah, we can start now. Arigna? Hello.
I think he's facing some issue in joining.
I think he has gone to the other room and he uh, may join soon.
Yeah,
Oh,
hi.
yeah.
Okay.
So, hello everyone. Welcome to the second session of invited lecture series by Professor Viji Thomas. We will continue with the yesterday's lecture. Over to you, sir.
Okay, thank you. So yesterday we had seen that ideals maximal with respect to some property happen to be prime. So, and one of the theorems we saw was Cohen's theorem, which said that R is a Noetherian ring if and only if every prime ideal is finitely generated. So if every prime ideal is finitely generated, then R was the ring is Noetherian. So we will generalize this and as a consequence obtain that theorem once again. So proof goes almost similarly and slightly more longer, but it's okay. Just a moment. Theorem. I hope you can see what I'm writing. I am not sure.
Yeah, it is visible.
Okay. It's a theorem of Jothilingam. The proof I give is not by Jothilingam. It's by I forgot the name. Okay. So let A be a commutative ring. So we will always have commutative ring. Our rings are with identity. Let A be a commutative ring and M be a finitely generated A module. Okay. Then M is a Noetherian A module if and only if PM is finitely generated A module for all primes of the ring. This should happen for all primes of the ring. Then M is Noetherian A module. So before going into the proof, let's look at the corollary. Take M equal to A above, then let's see what it reads. Then A is a Noetherian A module if and only if PA is finitely generated for all P. In spec means for all prime ideals of A. Huh? So that means A is a Noetherian A module is precisely saying A is a Noetherian ring if and only if every prime ideal is finitely generated. So this is Cohen's theorem. So we obtained yesterday's theorem, one of the theorems from yesterday, which was by I.S. Cohen as a corollary of this theorem. And yesterday I did present Cohen's theorem because now when I present this, this will not hopefully seem too long because the ideas are similar. Okay. Now let me see how to add a page. Since the proof is long, well, let me write at least the strategy. The strategy of the proof. Huh? Let's divide it into, say, three pieces. So step one. We will somehow find a submodule n. We will, the strategy will be to assume that M is See what we want to prove. M is not Noetherian A module. Okay, that is, see, if M is a Noetherian A module, then every submodule is finitely generated and PM is a submodule. So one direction is clear. So assuming PM is finitely generated, we have to show M is a Noetherian A module. So what we'll do is we'll assume, suppose it is not. Then, next page. So then what first step one, we will find a submodule maximal with respect to being not finitely generated. Anyway, we'll do the whole proof in a detailed manner, but I just want to write the steps down because otherwise the proof will keep going and I don't want you to get lost because it's going to take some time. Find a submodule maximum with the property of being not finitely generated. So we will find a submodule n of m such that it is maximal among non-finitely generated modules. Huh? So that is the first step. Step 2 will be, we will take the annihilator of the module m by n. This is an ideal and we'll claim that this ideal is a prime ideal. Okay. Annihilator is an ideal, is a set of all elements in the ring A which kills the module m by n. So in particular here, P kills m by n. This is precisely saying that if you PM is contained in n. Okay, so this is the second step. Last step, what we'll do is show that this n is finitely generated. This will give the required contradiction because our n was not finitely generated. It is maximal among ideals that submodules that are not finitely generated. And we will show that it is finitely generated. How will we show that? Assuming PM is finitely generated. So with this assumption, we'll show that finitely generated. N is finitely generated. And we'll get a contradiction. And that will finish the proof. So these are the 3 steps that we have to go through. And so let's begin the proof. Huh? So this was just strategy. I have not started the proof. Even though I wrote the proof here, let's delete this. So this is not the beginning of the proof. I just wanted to discuss what are the things that we'll try to do. We'll just follow these 3 steps. Okay. So let's begin the proof. So proof. Now this direction. M was Noetherian A module. So this is clear. Why is this clear? If M is Noetherian, every submodule is finitely generated and PM is a submodule and hence finitely generated. So this direction is clear. Now comes the real direction. And in this direction is where we need the 3 steps. So let's say, assume PM is finitely generated. This is what we are assuming. Okay. But M is not finitely generated. Is not Noetherian. So we assume PM is finitely generated, but M is not Noetherian A module. So now consider this set. N prime contained in M. N prime is an A submodule of M, which is not finitely generated. Okay, good. So we have a submodule of M which is not finitely generated. What can you say about this set S? Empty or non-empty?
Non-
Anything you can? Huh?
Non-empty.
Non-empty. Why? Because M is not
Not
Noetherian.
Noetherian.
Yeah. So note S is not empty. So this means what? By Zorn's lemma, what can you say? S has a maximal element. Say N. Okay. So this is our first step. So we have completed the first step. We have a submodule of M, which is maximal among submodules that are not finitely generated. So our step 1 is complete. So I'll go to the next page. Now let's write it as step 2. What was step 2? That we wanted to show that this P annihilator A M mod N is a prime ideal. Okay, good. So to show it's a prime ideal, we'll follow the same process like yesterday. What did we say? Suppose not. Then we have elements AB belongs to P, but A does not belong to P, and A does not belong to P and B does not belong to P. We have this. Okay, good. Now, notice this. Those who were present yesterday, I hope you can see. What can you say about this? This submodule of M. B is an element not in P. Huh? So this Bm is not in N. So I've given you the hint. So what can you say? It contains N. I want to say it strictly contains N. Why does it strictly contain N? Because Bm is not contained in N. Bm would have, see, ABM, so this means, let's look, AB belongs to P, what does it mean? AB belongs to P means AB kills M. AB, M is contained in N, but B does not belong to P. So BM is not in N. So BM, this is, so N plus BM strictly contains N is what I want to say here. Because BM is not in N. So it is, there are elements, I mean, it's outside. So it is a bigger module compared to N. Okay. So this is what first observation from it. All we are getting is this is strictly containing N. This kind of strategy we used yesterday also. Same kind of strategy. And so then what did we say in yesterday when we had something bigger? Yes. I'm waiting for some of you to answer.
That capital N was maximal with respect to
And so by maximality of N, uh, we have that N plus Bm is finitely generated. Say it is finitely generated by these elements. M is, let's say, A U1 plus dot 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 plus A UN. Of course, UI are in M, but let's write specifically how UI will look. UI is equal to, how will it look? CI plus BDI, where CI belongs to N and DI belongs to M. Correct? Is this fine? Okay. So let's remember this. Now what I want to do is, yesterday also, what was the another, if you want to consider the colon ideal. First, let me define what it is. Because that was, so it is submodule. Yesterday was colon ideal we defined. Here I am saying it is the set of all M belongs to M such that B times M lands in N. Huh? Check that this is a submodule of M. Of N. Okay, check this. Now, what can you say about this? I want you to notice this first now. N is clearly contained in this submodule. What else is contained? See, if we go by yesterday's strategy, and if we say there is some justice in the world, maybe we can say this also strictly contains N. That is what we want to do, right? Yesterday, N plus Bm strict. Now we showed that N plus Bm strictly contains N. And the colon ideal was also strictly containing. And then by maximality, we said it is finitely generated. That is the strategy we applied. And same strategy we want to apply. For that, we want to say that N colon Bm, this submodule contains N, and in fact strictly contains N, is what we want to say. Clearly, N is contained here. So let's go to the next page. Clearly, N is contained in N colon M, and I think it is B. Now, what else? How do we show that it strictly contains? Note that AM is also contained here. Why? Why is AM contained there? You multiply A and an element of M times B, then it will be AB times an element of M. And AB times an element of M, let's look. Here we had made this observation. AB belongs to P precisely means AB times M is contained in N. Okay. So next. So AM contained. Therefore, what we have observed is N is strictly contained in. This is what we are. Therefore, by maximality, N M B is finitely generated. Suppose, say, N M B is finitely generated. So let's say V1, that was U1, I believe. So this we'll call it VM. That was N indexed and this is M indexed. So let's call this star. It's fine. Okay. Okay. So claim. Now I want to make a claim. You tell me what the claim does for us. So let me go back. So we previous I have to go. So in here, N plus Bm was finitely generated by A U1 plus, this is A U1 plus till UN, and each UI are CI BDI. Okay. So what I am going to now say is that this claim N is A C1 plus dot 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 plus A C N plus, if somebody remembers yesterday's proof, what you should say is it's B times V1 dot 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 B times Vn. It should be generated like that. So A B V1 plus dot 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 A B Vm. Okay, this is what I want to claim. Now let's see. This direction yesterday was also very trivial. Let's see why it is trivial. Why is it trivial? Where do the Ci belong? Ci belongs to N. So all Ci belongs to N. So now next, Ci belongs to N, no problem. Now Vi belongs to this colon module. Okay. So that means B times Vi belongs to N. See, each of the Vi belong to this colon module. So that means what? B times this Vi will land in N. And B times Vi will land in N. So this direction is clear. Everything is in N. Now that means we have to take an element. So now we are going to go for this. Okay. By the way, what is the use of this claim? Let's at least before, so that you don't get lost in the flow of the proof. What would be the advantage? Suppose I prove the claim, what will happen? What is the advantage of that?
We will have a contradiction.
It becomes N is finitely generated, but N was not finitely generated, and it will contradict the fact that suppose not P is a prime ideal, and we would have proved that P is a prime ideal. So we would have achieved our step 2. Okay, so that is where we are headed. So I just want to make sure that you all know where we are headed. So N is this. So okay, let's take Z belongs to N, but N is of course contained in N plus Bm. Okay, so that means what? Z can be written as a summation I equal to 1 to N lambda I Ui. Remember Ui were the generators of N plus Bm. Let's go back previous. See, it was written like that. It is generated by U1 to UN, and each UI is Ci plus BDI. So that's what I will now replace. So this is nothing but summation I equal to 1 to N lambda I Ci plus what else? I equal to 1 to N lambda I B di. How did we get that? How did we get that? N plus Bm is finitely generated. So here we took an element of N. Of course, N is contained in N plus Bm, and N plus Bm, according to this, is finitely generated by U1 to UN, and each UI is Ci plus BDI. So it can be written as finite linear combination of these elements. So that is what we have done. Okay, good. So now let's observe. This belongs to N, and Ci, where did Ci belong to? N. So this summation belongs to N. That means what? This sum should be in N. Okay, good. So that's what we are going to say. So B times this sum I equal to 1 to N lambda I di belongs to N, because Z belongs to N and the Ci's belong to N. So when I subtract, the rest of this belongs to N. That is what we have done. Okay, good. Now let us next plus. So what have we written? So I'll rewrite what we had written earlier. B times I equal to 1 to N lambda I think di belongs to N is what we have written. Now what can you say? This means what? Yesterday, even till here, everything happens the same way as yesterday, if you remember the proof from yesterday. Till this point, everything is the same. So what should you conclude now? Therefore, I want to say, let me see if you can say it. I equal to 1 to N lambda I di belongs where?
Colon submodule.
Yes, the colon submodule. Because this whole element, which is in M, this is actually M, di were in M, if you remember. Let me remind you. See, di were in M. So this whole element belongs to colon because that times B is in M. So this belongs to colon ideal. Okay, but colon ideal was finitely generated. So what by some elements. So therefore, I equal to 1 to n, lambda I di can be written as what? Summation. I think it was indexed till m. So j equal to 1 to m, say nu j, and it was generated by Vj's. Huh? So what does z become? We started with z. Let's go back. So I want to write z was here. You see, z was written as lambda I ci plus this summation. And summation I equal to 1 to n lambda I di is now summation j equal to 1 to m nu j vj. So that's what we will just replace in here. That's all we are doing. So this is nothing but summation I equal to 1 to n lambda I ci plus summation, it is j equal to 1 to m nu j and b vj. Okay. So it is nu j vj times b. It becomes like this. So what have you shown now? We have shown what we wanted to. So therefore, n equal to what? N equal to AC1 plus dot 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 ACN plus what? A BV1 plus dot 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 A BVM. Right? This is what we wanted to prove. Claim, look. Here was the claim. And we have proved the claim. Okay? Therefore, N is finitely generated. Of M. But this is a contradiction. Because M was not finitely generated. In fact, M was maximal among submodules of, no, N was maximal among submodules of M that were not finitely generated. So this was contradiction. Therefore, P, which was written as annihilator, M mod N is a prime ideal. Note this, so far I have not used the hypotheses that PM is finitely generated. At the moment, I have not used. So now we will use. Huh? So at the moment, step 2 is complete. So that means plus. Step 2 is complete. Okay. Now step 3. We'll again prove that N is finitely generated, which will contradict that N was not finitely generated, and our original assumption that M is not Noetherian A module will be contradicted, and we'll get M is a Noetherian A module. And that is what we want to do. This is where we are headed, and this is the final. Now we will start. This we have not used yet. M is a finitely generated A module. Say M can be written as A x1 plus dot 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 A xr. If M is finitely generated, then any quotient of M is finitely generated. This is a very easy fact. So M by N is finitely generated by x1 bar plus dot 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 plus A xr bar. XR bar means what? Xi plus N, coset of Xi in M mod N. So this is. Now, here is a fact that I'm going to use. So therefore, P, which is the annihilator of the M by N, of the A module M by N, when a module is the sum, annihilator becomes the intersection. This is a simple exercise. I will leave it to you. If you have a module which is sum like this, and if you are considering the annihilator of that module, then it becomes intersection I equal to 1 to n, annihilator of AXI bar. XI bar. Okay. Okay. Now I want you to make an observation
It
here.
should be 1 to R.
Oh, sorry. Good. Very good. 1 to R. Where is the eraser? It is not N. Everywhere we were writing N, and I also wrote it. It is 1 to R. Okay, good. So AXI bar. Good. Now I want you to make an observation about prime ideals. See, now you have a prime ideal which is intersection of ideals. So what can happen? One of them. Yeah, why is that? Let's look. Here I'll write. So if you have a prime ideal which is intersection of two ideals like that, then P is the has to be one of the ideals. It's easy to see. You don't have to worry. Maybe I should quickly show. So if P contains IJ, so what is means? See, what was the definition of prime ideals? It is in terms of elements. If AB belongs to P, then A belongs to P or B belongs to P. But it can be generalized to ideals also. If P contains a product IJ, then P contains I or P contains J. So this implies P contains I or P contains J. Okay. Now, P is the intersection. So P is contained in I and P is contained in J. But on the other hand, by definition, we got P contains I or P contains J. So we in together got P equal to I or P equal to J. So this is why. And you have to just do induction for R numbers. We have done for 2. Okay. So this is the reason. So because P is a prime, because P is a prime ideal, P equal to annihilator of AXI bar for some I. Okay. So what I wanted to take from here is if P is intersection of kind of ideals, two ideals, then P has to be equal to I or P equal to J, and we give the proof down here. Okay, so this is what we are using. So P is this. Now, okay, this means what in terms of elements? What can you say about? I just want to make an observation. See, Xi bar means what? Xi plus N. Xi plus N. N, not M. Xi plus N. So P times Xi will go where? P times Xi. So you have to observe that P times Xi will land in N. Contained in P is the ideal, is contained in N. Why? P is the annihilator of Xi plus N, means it is the annihilator of that single element Xi plus N. So Pxi plus N is the zero element in M mod. So it is equal to N. So Pxi belongs to N. I mean, is contained in. So this is, yeah. Okay, good. So plus. Now we want to make another observation. N is strictly contained in N plus AXI. Why? Why it is strictly contained? Previous. See, Xi doesn't belong to N because we have assumed AXI is among these generators here. If there were less, one of them was in N, then this would be a less number and that would not be the element that we would be picking. So Xi is not in N. Next. So this is strictly contained. So now what can you say? Again, you have something bigger than N. So therefore, by maximality, n plus a xi is finitely generated A module. Okay. So let's assume it is finitely generated by n plus a xi. Suppose it is finitely generated by, I will just write yi plus say r I. No, let's write out the elements. Rxi dot ys, maybe s has not been used, plus rsxi. Why I have written the elements of this form where yi belongs to n and ri belongs to a. Right? It is finitely generated. Okay. So let x belongs to n. Huh? Let's start with x belongs to n. Okay. X belongs to n. Of course, n is contained in n plus axi. Strictly contained. So every element x is contained, this element x is contained in n plus axi. But n plus axi is finitely generated. So I can write this as a finite linear combination of those elements. And that's the strategy I'll use, just we have used before. X is equal to a1, y1 plus r1 xi plus dot plus we have s of them. So as, ys plus rs xi. Good. So this can be written as summation ai yi, I think I equal to 1 to s, plus, now is interesting, xi, I want to see who will answer. I have a question. I equal to 1 to s, as rs. Huh? And this is x. Now this belongs to n. Okay. And yi belongs to n. So this also belongs to n. Okay. Therefore, this summation I equal to 1 to s, as rs, and then this xi is there, belongs to n. Clear? This much is clear. Now, if this belongs to x, what can I say about summation as rs? This is what I want to ask. This is my question. Yes, this is the interest. This is what I want to ask. Yes. But no, n colon xi, I have nothing known about it. Yes, that is, so I can't use n colon xi. Yes, that is right. But let me remind something. This is where it is interesting slightly. See, let me remind. P was what? It was in the earlier page, but I don't want to go back. P is annihilator of a xi bar. So that meant what? We had made an observation. This means P times xi belongs to n. Previous somewhere we have done. Pxi belongs to, is contained in n. Huh? So next. So now can you say? From here,
This
because
summation annihilates the xi bar.
so that means this summation has to belong to P. P is the annihilator of xi. And this is annihilating. So therefore, this implies this summation I equal to 1 to s, as rs belongs to P. Okay. So plus. Now let's write what was. So what have you written? So let's go back. So this, so every element n we have written as ai yi plus an element pxi. Huh? So that is what I'll write. So next, so every element n was written as ai, let's look, AI, yi, and AI is in A. So we have basically written as y1 plus dot 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 plus ys plus p xi. This is what we have done. Okay, this is the equality we have proved. Right hand side is contained in the left is clear because each yi are belonging there and p xi is in n. So that is in n, and n is contained here also. That is the calculation we did. So n is so this direction calculation is what we did in this previous page. Okay, this calculation shows that this containment. Now, this containment, this belongs here is trivial because each yi belongs to n and pxi belong to n. So this is also trivial. So this gives equality. Okay. So let me erase this part so it is out of the board here. Okay. So this is what we got. Okay. Now, we have yet not used that PM is finitely generated. Now will come. A y1 plus dot 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 plus A ys plus where was xi? Where were xi? Let's go previous. Xi was in previous. Xi was in M. Okay. Okay, good. So this is contained in Pxi is contained in Pm. Do you agree? Xi was contained in M, so Pxi is contained in Pm. Good. This is contained in Ay1 plus dot 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 plus Ays plus Pm is contained in where? Let's remind ourselves. P was a prime ideal. We had proved first step. Anyway, that is not needed here. All I need is P was annihilator of M by N as an A module. This implies actually Pm is contained in N. So this is contained in N. Now, this is contained in what? Where are yi's? Let's look. Previous. Where are our yi's? Yi belong to N. Okay. So next. So these are all in N and this is also in N. So this is whole in N. So what has happened? We have squeezed this between N and N. So therefore, N equal to A y1 plus dot 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 plus A ys plus Pm. Now, can you help me finish? I think the proof should be clear from now. How do you prove? What was the hypothesis that I said we have not used yet? Pm is finitely generated. So it is this, the first part is A y1 to ym. This is finitely generated. Now Pm is also finitely generated. So N is finitely generated. Since Pm is finitely generated A module, N is a finitely generated A module. And that is the contradiction. Because N is not finitely generated. Therefore, our assumption that M is not Noetherian A module is incorrect. So M is a Noetherian A module. Okay. So that's the kind of end of the proof. And we are done in both directions. So I hope this is clear. Now I just want to see whether, I mean, it's up to you whether you want to see. I would like to have given, but I don't know what is the time. Oh, it's not even 1 hour, right? So I have 10 minutes. Maybe in 10 minutes, I can show the proof of Eakin-Nagata.
Yes, sure.
Yeah, so maybe I will do this. So maybe at the end, you can ask question. Maybe let's go to Eakin-Nagata. Maybe it's a very nice theorem as a consequence. Eakin-Nagata. Let A containing B be commutative rings with identity, of course. To see different proofs of this theorem, you can, of Eakin-Nagata, you can look at Matsumura's book, and there is a proof there. But this is slightly different now that we will obtain it as a consequence of Jothilingam's theorem. So A be commutative rings, and B is a finitely generated A module. This is the hypothesis. If B is Noetherian, meaning if B is a Noetherian ring, then A is Noetherian. Then A is a Noetherian ring. That is a conclusion. Huh? Okay. The beautiful part is that the converse of this is very easy. Meaning if A contained in B is commutative rings with identity, and A is contained in B means A and B share the same identity, and that B is finitely generated. And if A was Noetherian, then B is Noetherian. This is a simple exercise. Let's go through very quickly. I will not say, so I'll let you think about it. So if we have this contained in A is contained in B, and B is finitely generated A module, and if A is Noetherian, then B as an A module is Noetherian. Once B as an A module is Noetherian, B is a Noetherian ring, because you take any ideals, ascending chain, that becomes submodules, and then that was already Noetherian, and so we'll get the converse is very easy. So the converse of the easy part is what the Eakin-Nagata is. Huh? So the converse is a easy trivial exercise. The proof of this, so converse of that trivial exercise is this theorem, and that requires a little bit of proof. So suppose B is finitely generated A module. Suppose we'll start B equal to A B1 plus ... ABN. Huh? Because B is finitely generated A module. Because of that, I can write this. Okay. Now consider this map. It's very good. A to say direct sum of B's I equal to 1 to n. Okay. How do you map? There is a very natural one. R going to RB1 ... RBN. Okay. Now, what can you say? Let me ask you one thing. Annihilator, what can you say about the annihilator of the module A module B? Can somebody tell me? So B is an A module. B is also a ring, and A is a ring. So what can you say about the annihilator of the B module, A module B?
All
Annihilator.
the generators should be annihilated.
Huh?
All the generators should be annihilated. So it will be the intersection.
No, that true. But see, so annihilator means what? If there was an element R in this annihilator, R belongs to A, then it should annihilate every element of B, right? So in particular, it should annihilate the identity also. But the identity also belongs to A. So R times 1 is R, it will be 0. So the annihilator, because identities are shared, is actually 0. This is the first observation. This implies that phi is injective. Okay, because as somebody was saying, that is the intersection of all this. Annihilator is nothing but that is already 0. So because the kernel is the annihilator and annihilator is 0, so phi is injective. This is the first observation. Okay, so this is the first observation. Now what we want to say, uh, uh, so phi is an injective A module morphism. That is what we have seen. Now what we want to do is we want to take P belongs to spec A, meaning P is a prime ideal in A, and we want to consider what is PB. Okay, so since B is Noetherian, what can you say about PB?
Finitely generated.
Very good. PB is a finitely generated ideal. Very good. I want to transfer this into now B is Noetherian ring means what? I'll write the same statement again. This is the equivalence of the same statement. So B is Noetherian means B is Noetherian as a B module. Okay, B is a Noetherian ring means is Noetherian as a B module. Okay, so what can you say about PB? Therefore, PB is a finitely generated B module. Now, let me write the statement and I will tell you why. Therefore, PB is a finitely generated A module. You may wonder how this is coming, but this is a very simple fact. Let's say if you have morphism of rings, commutative rings, the homomorphism of commutative rings of A to B. B is finitely generated A module, and M is a finitely generated B module. Then B is finitely generated A module. Okay. So from there, you can get that PB is finitely generated A module. But PB is finitely generated A module. P was an arbitrary prime. We took, this is for all P belongs to spec A. So what can you say now? Can you say something now? We just proved something. What have you got? PB is finitely generated A module for all P. What did we prove? If PM is finitely generated A module for all P, then if PM is finitely generated A module for all P, then M is a finitely generated A module. So here, what should I conclude? Therefore, by Jothilingam's theorem, B is a Noetherian A module. This is where Jothilingam's theorem, we are concluding B is a Noetherian A module. Because we have proved that PB is a finitely generated A module for all P. Therefore, B is a Noetherian A module. Okay. Now, we are to the almost final stretch. Let's remember the first homomorphism. This is an A module homomorphism, I equal to 1 to N. Huh? Now, B, what we proved, B is a A module homomorphism. B, we have proved previous page, B is a Noetherian A module. And it's a fact, or we will learn, or if you have not learned, that then direct sum of B is a Noetherian A module. right? Therefore, A is an A submodule of a Noetherian A module. This was injective. So A is a submodule of the Noetherian A module, this direct sum of B's. So what can you say? A is a submodule of a Noetherian A module. So A is Noetherian. Therefore, A is Noetherian A module. Therefore, A is Noetherian ring. And that's the end of it. That is what we set out to do. So I think I have taken exactly 1 hour. Yes. So yeah, so I think that's the end of the proof. And if you have questions in Jothilingam's theorem or this, you can ask. Or you can email me. So this was Eakin-Nagata. And it was a consequence of Jothilingam's theorem. And this was Jothilingam's theorem. But I have given a proof that we used to prove Cohen's theorem. And as a consequence also, we obtained Cohen's theorem. So this proof is, I forget the name of the person, but yeah, and it mimics almost the proof that I gave you for Cohen's theorem yesterday. It almost mimics. If you go and compare, you will see that it's a kind of the same proof. It goes a little longer because it's more general theorem. So that theorem was for rings. This is a theorem for modules. So this is a more general theorem here. and this, yeah, as a consequence, we obtain Eakin-Nagata. Okay, so I will stop here.
Okay. So, do you have anyone have any questions at this moment?
Sir, hello, sir.
Yes.
Sir, is there any similar result like maximal prime principle in non-commutative rings?
Maximal implies prime in non-commutative. I have not seen some, maybe 1 or 2 results may go, but I have not seen it. No.
Okay, sir.
But perhaps it goes through also for non-commutative. So I have to check. I am not sure of the top of my mind. I have not myself gone, but maybe some of these results could go. I think the same paper, the guy, Manuel Reyes, that I yesterday pointed out, maximal implies prime. I don't know how many of you looked at the paper. It was the T.Y. Lamb, Manuel Reyes paper. And he, I think, subsequently wrote, and maybe he wrote for non-commutative rings also. I have to check, but I am not sure about it.
Okay, sir. Thank you. Thank you.
Anyone other? Okay, so if there is no more questions, let us thank Professor Viji Thomas for these 2 beautiful sessions. And thank you everyone for joining both of the sessions. And I hope you have enjoyed it. Special thanks to MTTS Trust and everyone who made the sessions possible. So before we conclude, can we turn on the video so that we can take a group photo for today?
Yeah, so
Jyoti, can you take the photo?
Okay. So on the countdown of 3, we will click the picture. Okay, so sir, before that, can you stop sharing? Yeah.
oh, stop sharing.
Yeah.
Yes.
Yeah, it's done. Okay, so 3, 2, 1, smile. Yeah, thank you.
Hi, Shamik. So you are here.
Hey, hi, Viji. Very
Good.
nice result, actually. I've not seen this before. It was a new thing for me, like this
Good,
kind
good.
of
I'm
argument.
glad. So I'm glad at least it was new for somebody. Yeah, but yes, I hoped it was new for many of the students, but good that was also new for you. Uh, so I also see, I think Amit, no, yeah, somebody wrote to me Amit, and then I also see Amit Fogart. Yes, I also know him. Okay, okay. Thank you. See you.
Okay, so before we conclude, there is a final feedback form shared with everyone. Please fill the form before 11 a.m. tomorrow, and please do not forget it. And the next talk is on March 1 by Professor Sujata Ramandoray. I hope to see you all there, and thanks once again, and have a good day, everyone.
Okay, thanks, Viji. Yeah.
Yes, Chaitanya, you can end the meeting. Hello.